Okay, so this is a video that talks a little bit about Snell's Law, just an example of a Snell's Law problem. This is the setup as you're always going to see it. Maybe it'll be horizontal, but the idea is you start in one material, N1, and you go to another material, N2. Originally, the light ray comes in making some angle with the normal. This dotted line is called the normal, which just, again, means perpendicular to the surface. You come in at some angle theta 1, you leave at some other angle theta 2, right? Now, the way I've drawn this here, N2 is greater than N1. And I know that that's the case because my light bends toward the normal. In other words, theta 2 is smaller than theta 1. That means that the light is bending toward the normal line. That happens when you go from low index to high index. If you want to know what happens when you go from high index to low index, well, just pretend that the light is going the opposite direction. Light, the way you draw these rays, it doesn't care which direction it's going. But here, when you go from high index to low index, well, look what happens now. Now it bends away. It bends away from the normal. And so the opposite of what we said is true. If you go from low to high, you bend toward the normal. If you go from high to low, you bend away from the normal. In other words, this picture gives you both cases. It's not one case, it's both cases because light doesn't care which way it's going. Okay, so how do you apply this to a problem? Well, I might say something like light comes in with an initial angle of 32 degrees, and it starts out in air, which has an index of refraction of 1, and it goes into water, say, which has an index of refraction of 1.33. Okay, so this would be given to you in some paragraph or something, and then, well, what do you do with it? Well, what you do is typically you find theta 2. How much does the light bend? Okay, so how do you do that? You use Snell's law. So N1, that's where we start. That's on this side. So N1, 1 times the sine of theta 1, which is 32 degrees, equals 1.33 times the sine of theta 2, whatever theta 2 is. So, okay, we do a little bit of arithmetic, and then theta 2 is the arc sine of 1 divided by 1.33 times the sine of 32. And you punch that up on your calculator, and so long as you are in degree mode, you'll get the right answer. Now, there's kind of a funny thing that happens when you go from high index to low index. Remember, we said that when you go from a high index of refraction to a low index, you bend away from the normal. And that's exactly what's happening here. This angle is small. This angle is big. You're bending away from the normal. In this case, this is almost like 70 degrees. You're coming in at, 40. You're leaving at 70. You're bending away because the white area has an index of refraction of 1. The blue area has an index of refraction of 1.44. But if you just play around with this sim's available in the module, by the way. This is the p-hat sim. If you keep tweaking this, look, the line keeps bending farther and farther away from the normal. You might wonder, wait a minute, what happens if I run out of angle? In other words, what happens when I get to 90 degrees? Well, when you get to 90 degrees, you've reached what's called the critical angle. In other words, your refracted ray makes an angle of theta 2 equals 90 degrees. And under those conditions, since the light can't refract anymore, it doesn't refract at all. All of the light gets reflected, and it follows the normal rule of reflection, which is angle of incidence equals angle of reflection. So it comes in at 45 degrees and it leaves at 45 degrees. It's just normal reflection. If I go smaller than the critical angle, well, then some refracts. As soon as I hit that critical angle, boom, you get nothing on the other side. And so this is called total internal reflection. So this is what total internal reflection looks like. Your refracted angle, theta 2, is 90 degrees. 90 degrees at the critical angle. If you go beyond the critical angle, in other words, if you continue to sweep this guy out at a bigger angle, then you'll still have total internal reflection. But the critical angle, theta c, theta 2 is 90 degrees when theta 1 equals the critical angle. Okay, and so, I don't know, a question you might get that might look like this might say something like, if N1 equals 1.6 and N2 equals 1.3. Find the critical angle. In other words, what is the biggest that this theta 1 can be so that light will be transmitted? Another way to say that is, what's the maximum angle you can have before total internal reflection? So that's to say N1 times the sine of theta critical equals N2 times the sine of 90 degrees, because it is defined, the critical angle is defined as theta 2 equals 90 degrees. So then you have 1.6 times the sine of theta c equals 1.3 times 1. So what's theta critical? Well, theta critical is the arc sine of 1.3 over 1.6, and that is some number. If you're in degree mode, you'll get the right answer. If you're in radian mode, you won't. One important thing to think about, though, is this only works if N1 is greater than N2. What happens if you try to do this kind of a problem going from low index to high index? In other words, what would happen if this number were smaller than this number? So let's just pretend for a second that I said 1.3. Let's go the other way. 1.3 times the sine of theta critical equals 1.6 times the sine of 90. Well, then in that case, you would have the sine of theta critical equals 1.6 divided by 1.3. And if on your calculator you tried to solve this for theta critical equals sine to the minus 1 of 1.6 over 1.3, your calculator would say error. And it's not because the physics is wrong or the calculator, you've made a numerical mistake. It's because the sine of theta is always less than 1. Sine of theta is less than 1. This is bigger than 1. So this is not possible. Well, what does that mean for us? It means it's not possible to go from low index to high index and see total internal reflection. You have to do it this way. You have to go high to low. Okay, hopefully this was more helpful than confusing. Feel free to ask questions on the board if you are confused.